we're going to get started in a new chapter, chapter 9. The title of this chapter is the quadratic reciprocity law. Roughly speaking, the quadratic reciprocity law is concerned with actually solvability of the quadratic equations. That is means, of course, congruent quadratic equation. So we're going to start with section 9.1, and in it we're going to prove a criterion called Euler's criterion that determine whether an integer is what is called a quadratic residue or a quadratic non-residue modulo an integer n. So we're going to start with, since the title, which we say the quadratic reciprocity, has something to do with the quadratic congruence equations. So we're going to start with giving a necessary and sufficient condition for the solvability of the quadratic congruences. Then we're going to move to define this concept of quadratic residue and quadratic non-residue modulo any positive integer n. Then we're going to state and to prove Euler's criterion. And gives for a given integer, all right, give a conditions under which this integer is a quadratic residue or quadratic non-residue modulo an odd prime, only for odd primes. Then we're going to determine the number of quadratic residues and the quadratic non-residues for any given odd prime. Then we move on to proving that any quadratic congruence mod an odd prime has either zero solution, it has no solutions, or exactly two incongruent solutions. Then we're going to give an alternative or a second proof of Euler's criterion, and the proof that was given by Burton. It's a little long, but it is actually an interesting proof. All right. Again, it's a very big list. Hopefully, we can go through the whole thing in one lecture. So let me start with preparing for giving a necessary and sufficient condition for a quadratic congruence equation to be have a solution or no solution. So we're going to consider the general, consider the quadratic congruence equation. Ax squared plus bx plus c congruent to 0 on b. So we're going to consider it where b is a prime. All right. In order for this actually to be a quadratic, we require also b not to divide a, because if e divides a, really this is equivalent to saying that a is congruent to 0 mod b. Basically, mod b, the a is equal to 0, and the equation becomes bx plus c congruent to 0 mod b, a linear equation. And we dealt with linear congruence equations in chapter 4, so we don't want to go through this. All right, so these are the conditions that we want to put on. Of course, the A, B, and C are all integers, all right? All right, now we know that by Lagrange's theorem, the quadratic congruence equation has at most two solutions, two incongruent solutions. Now, first we're going to look at the case where P is the even prime 2, and we're going to see that actually it's going to be the case where we could have one solution, no solutions, or two solutions. And then in the case where P is on R prime, we're going to actually show that either we're going to have a unique, no solutions, zero solutions, or exactly two incongruent solutions. So in other words, the even prime 2, it's an exception because it doesn't follow this actually nice kind of characterization, no solution or two solutions. So all right, so let's look at the case where assume that P is equal to 2. Then the possible quadratic congruence equations in this case so let me list them. Means the coefficients, the A, B, and C is going to be either 0 or 1, all right? Because everything else we can reduce mod 2, so we cannot have 3 or 4 or even 2, all right? So it's going to be x squared congruent to 0 mod 2. Then we have x squared plus 1 congruent to 0 mod 2. Or we could have x squared plus x congruent to 0 mod 2. And one other form where we have x squared plus x plus 1 congruent to 0 mod 2. So these are all the possible combination that give us a quadratic equation mod prime 2. Now, in this case, this one has a unique solution as one solution. Of course, namely x is congruent to 0 mod all multiples of 2 as far as integers. Those are congruent to 0. For this one, we have actually x congruent to 1 mod 2. Again, unique solution. This case has actually x equal 0 and x equal 1. So it has two solutions. And x congruent to 1 mod 2. And this one has no solution. But again, the only solutions it is going to be either we need mod 2 here, is either 0 or 1. So when you plug in either one of these, it's not going to satisfy this. So these are this. Now, as I said, this is the exception, all right? On the other hand, for any, we will show later on, we will show later in this lecture actually for any prime p that does not equal to any quadratic congruence equation has no solution or exactly two incongruent solutions mod p. All right. With this, now let's look at the case where p is actually an odd prime and find a criterion or what we call a necessary and sufficient condition for its solvability. So, because the case for p equal 2 is trivial, we actually look at all possibilities. So we're going to look at the general case for odd primes. All right, so we have this theorem. Actually, this is in the book. They did not put it in the form of a theorem. They put it in the form of a discussion. So I'm just going to actually write it as a theorem, so you know what is given and what is, what are the conclusions which you can get from these given assumptions. Okay, so I'm going to let p be an odd prime. And ax squared plus bx plus c equivalent to 0 mod p a quadratic congruence equation where p does not divide. Then the congruence equation has solution if and only if the simple quadratic congruence equation y squared congruent to d mod p, where p is equal b squared minus 4ac. I guess you are familiar with this quantity from the quadratic equation where real number has coefficients called the discriminant of the equation. So we are saying that the original equation is going to have a solution if I only have this simpler, okay, quadratic congruence equation, y squared congruent to d, where d is given by that, has a solution, So this is the necessary and sufficient condition for the solvability of the original equation. And really, this is not very unusual. The idea is basically when you even take in a regular quadratic equation, all right, the algebra quadratic type equations, you do what is called completing the square. And completing the square is basically transforming the equation into something like this, y squared, where y is going to be, of course, written in terms of the coefficients a, b, and c. All right. Moreover, and this will actually appear in here. Moreover, for each solution, y sub 0 of y squared congruent to p mod p, a solution x sub 0 of the linear equation or congruence equation, which is 2ax plus b congruent to y sub 0 mod p gives okay, so a solution for this linear equation gives a solution to the original congruence equation, which is ax squared plus bx plus c congruent to 0 on. In other words, this theorem is basically tell us how it's sort of a procedure, how to solve a quadratic congruence equation by transforming this into a simple quadratic, and in solving this simple quadratic for every solution, because this actually we're going to see that it does have two solutions, and for each one of these solutions, we find a solution for this linear quadratic, and then this would actually produce or give us the solution for the original equation. All right, so this is more of two things. It tells us, the conditions under which the equation is solvable, and at the same time give us a procedure on how to solve. All right, let's go ahead and prove this. So remember, this is an if and no if. So let's just start with assuming that we have a solution. Okay, so let's start with the proof. We're going to go this way, that x sub 0 will be a solution to ax squared plus bx plus c congruent to 0 mod. satisfies the equation. So this implies x sub 0 satisfies that equation, which means we have ax sub 0 squared plus bx sub 0 plus c equal to 0 mod d. This actually does hold. We have an actual, all right, congruence relation. All right, now we know that since B does not divide A and B is odd, this implies B cannot divide 4A, right? So what does this mean? This is equivalent to saying that 4A is not congruent to 0 mod B. Then I'm going to multiply this congruence relation by 4A. It's like I'm not multiplying by 0. That's the significance of this. So we're going to multiply we call this one in here a star, right? So we're going to multiply both sides of the star by 4A, and this gives us 4A squared x sub 0 squared plus 4A b x sub 0 plus 4ac, and this is congruent to 0 mod b. Then I want to do one other thing. I want to add and subtract b squared. Add and subtract b squared to the last congruence. And this would imply, upon arranging the terms of this, so it's going to be 4a squared x sub 0 squared plus 4ab x sub 0 plus b squared. So this is when we're adding, and then I'm going to subtract the b squared and take it to the other side of the congruence minus 4ac. And this is mod. The expression on the left-hand side is a complete square. So this one is actually 2a x sub 0 plus b squared. And this is congruent to b squared minus 4ac mod b. And remember, all of these congruence relations, all of these are whole because we are having for a specific value all of these numerical values, including the, of course, the x sub 0. Now we're going to let y sub 0 equal 2a x sub 0 plus b, and we're going to denote the d to be the right hand side mod b. So this would imply, of course, that so this notation, this implies y 0 squared is congruent to d mod b is whole. And this is equivalent to saying that the quadratic congruence y squared congruent to d mod d has a solution, which is of course y sub 0. All right. Now, let's go the other way around. Let's assume that so conversely, going the other way around in the proof. So conversely, assume that y sub 0 is a solution to y squared congruent to d mod. Then we're going to consider the linear congruent equation to a x plus b congruent to y sub 0 mod d. So we do have a numerical value for y sub 0 in here. Since the greatest common divisor of the coefficients of x, which is 2a, and the modulus b, this is equal 1 because b is an odd. This implies that linear congruence equation has a unique and, okay? And since we also have, of course, and 1 divides y sub 0, this implies the linear congruence equation has a unique solution. Has a unique solution. Let's say x sub 0. So now we have so I'm going to show that actually this x sub 0 is the solution for the original equation. All right. So this implies, of course, that 2a x sub 0 plus b congruent y sub 0 mod b, this holds. All right, and with this, we also have the remember that this satisfies d, okay, which is equal b squared minus 4ac. All right. Actually, this one is mod. We also know this one does hold. Now let's put this together. This means that when I square this, this becomes congruent to y. This is y squared, y sub 0 squared, all right, and y sub 0 squared is congruent to the b squared minus 4ac mod b. Also this called, and this of course gives us the original equation almost after we divide. So this is equivalent to a square x0 square plus 4a x sub 0 b plus b square. All right? So this is congruent to b square minus 4ac on b. And again, we can cancel the b square. This is really where we started. And then we can divide by, by 4a because it's relatively prime to b. And when we get in here, we get a x0 square plus b x0, and then bringing the c to this side, and this way. All right, so in other words, we did show that x sub 0 is a solution to the original equation. All right, now, as I mentioned, this quantity d, all right, play an important role in the solvability of quadratic congruence equation, as it does in the case of regular algebraic equation with real numbers as coefficients. Remember, in the case of regular quadratic equation, D determines the character of the solution. Either we're going to have real solutions, two distinct real solutions, or one, all right, or complex solutions, depending on if the discriminant is positive, negative, or zero. All right? In the case of quadratic congruence equations, D equal b squared minus 4ac. All right? This determines whether a quadratic congruence equation ax squared plus bx plus c equivalent to 0 on b has a solution or no solution. And remember, this is what we have shown. If y squared congruent to b mod, sorry, d mod b has solution, this implies the original congruence has solution. Or actually, we'll say that this one has solution or has solution if and only if ax squared plus bx plus c equal to 0 mod b has solution. Or not, of course, because in a fan only f, so if this doesn't have a solution, this doesn't have a solution, and good version. All right? So in other words, what we want to be concentrating on the remaining part of this section is to look at this special type of the quadratic congruence equations. And we actually have a certain, particular terminology which we use for this kind of congruences. And this is what we call, an integer being a quadratic residue or quadratic non-residue. So this one is going to lead to this definition. All right? Actually, we have defined this concept earlier in section 8.4. Even we define what we call K, power residues. and non-residues. So here we're going to specialize for quadratic. All right? So we're going to start with let n be a positive integer. So we're going to do this one for any integer, not necessarily just odd primes or even primes, just any integer. So let n be a positive integer. And integer a, relatively prime, to n, sorry, is called a quadratic residue of n or mod n if the congruence equation x squared congruent to a mod n has residues. On the other hand, if x squared congruent to a has no solutions, mod n, of course, and has no solution, then a is called a quadratic non-residue. Or I want to make this remark concerning a very little technical issue. Concerning residue and non-residue. Here is the remark. If A is congruent to 0 mod n, then x squared congruent, actually, we could say A mod n as x congruent to 0 mod n as a solution. So in other words, if that satisfies as a solution. However, the greatest common divisor of A and n, remember n is a positive integer, and we cannot have A and n be 0, so this becomes greatest common divisor of 0 and n, same, and this is equal to 0, not equal to 1. So in other words, 0 is not relatively prime to any positive integer, n. So for this reason, we don't consider any integer A such that A is congruent to 0 mod n to D, a quadratic residue or a quadratic non-residue. Residue or non-residue. For any integer or any positive integer. So in other words, it violates one of the conditions we impose on A to be relatively prime to the integer that we are considering, this A is quadratic residue with respect to or quadratic non-residue. All right, so this is something just kind of a very trivial technical issue in here. We don't need to worry about it very much. All right, let's look at actually an example how we would go ahead and solve a quadratic congruence equation. Just apply the method of the theorem. All right. So here's an example. So let's look at 3x squared plus x plus 3 congruent to 0 mod 7. Solving this quadratic equation just to solve it, it's really not very hard. We could try, what we call it, trial and error by substituting for x by a complete, complete residue system for 17. Okay, 0, 1 up to 16, and see which one actually satisfies. But this method is, which we call brutal force, is not going to be effective, of course, if the modulus is very, very big. All right, so in other words, we need more effective methods of doing this. And that's what we eventually going to find out. The quadratic reciprocity law is going to help us. The calculations we're doing here are not very practical, but at least it will illustrate the ideas. All right, so this one we look at that simple. We're going to consider the simple quadratic, which is y squared congruent to d on 17, where d is equal b squared minus 4ac. Here, when you do the calculation for this, you're going to find this is equal negative 35. So you're going to consider this equation mod 17, and in a sense, okay, it's kind of give you a heads up. We are trying to find, the square root, basically, of negative 35 mod 17. In other words, is it actually there is a perfect square, basically? And we're going to find out yes it is. All right. First of all, we can replace this by this equation, which is congruent to negative 1 mod 17. So negative 35 is congruent to negative 1 mod 17. Now, solution for this, and again, I say we're going to basically do trial and error in here, solutions for the last equation. Going to be y sub 0 is congruent to 4, any integer, and 30. So these are the two incongruent solution mod 17. So these are not congruent, these are the mod 7. Now, next we consider for each one of these, we consider the linear congruent to ax plus b congruent to y sub 0. Let me start with 4 mod 17, and we're going to do this one for 30. So in this case, this equation, the a is equal to 3, the b is equal 1, so the equation becomes the linear congruence equation becomes 6x plus 1 congruent 4 mod 70, and the other one which corresponds to 13, it's going to be 6x plus 1 congruent 13 mod 7. It's not very hard to see that each one of these is going to have a solution because 6 and 17, they are the greatest common divisor is 1, and we have a unique solution similarly for this. Now the solution for this, again, we could apply the methods we learned earlier, or just a trial and error in here. For our purposes at this stage, this is 9 mod 17, and the solution for this is congruent to 2 mod 7. And these are solutions for the original. So these are solutions to 3x squared plus x plus the 3 congruent to 0 mod 7. And we have done, so we found the exact two solution for this. All right. Now, our next objective is actually to find a necessary and sufficient condition for an integer a to be quadratic residue or quadratic non-residue, since these are going to be the important factors in determining the solution of any quadratic equation. All right. So this is our next objective, is to determine whether a given integer. So here it is. So we're going to next objective is to determine whether a given integer a relatively prime to an odd. We're going to do it actually for odd primes, for an odd prime b. Because later on, we're going to learn that solving any quadratic or actually polynomial type congruence equation for a modulus that is not a prime, it's a matter of solving system of polynomial equations with prime factor, with modulus primes, the different prime factors of the number, and then use the Chinese remainder theorem to find the solution of the original congruence equation. So it is crucial that we only need to know eventually about just the primes. All right. So this is what we would like our objective is to determine whether a given integer relatively prime to an odd prime P is a quadratic residue or non-residue and this was given by Euler, okay, and in fact we did discuss it in the previous section. Here we're going to give another proof for it, and here it is. All right, so this condition was given by Euler. So this is called Euler's criterion. So this is theorem 9.1. Called Euler's criterion. Looks like this. Again, let E be an odd prime. And A an integer. Such that greatest common divisor of A, B is equal to 1. Then A is a quadratic residue of P if and only if this congruence holds. A to the power P minus 1 over 2. Remember that P is an odd prime. So P minus 1 is even divided by 2. So this is an integer. This is congruent to 1 mod P. And in a corollary to this theorem, we're going to show that if this A to the power P minus 1 over 2 is congruent to negative 1 mod P, then A is quadratic non-residue. Okay, so this is the original theorem, and the corollary to this gives us for non-quadratic residue. All right, the proof is gonna, let's again start with assuming that A is a quadratic residue. So let me actually start with the proof here. Assume that A is a quadratic residue of P. And this implies that x squared congruent to A mod P has a solution. Let's say x sub 0. So this means that this implies x sub 0 squared is congruent to A mod. Now, since A, B, the greatest common divisor is 1, and A x sub 0 squared is congruent to A, then this implies the greatest common divisor of x sub 0 squared and P, which is the same as greatest common divisor of x sub 0 and P is equal to 1 as well. All right? Now we're going to apply Fermat's theorem to this integer x sub 0. since x sub 0 and p equal 1 by Fermat's theorem, we have x sub 0 to the power p minus 1 is congruent to 1 mod p. All right. Then I'm going to take this This implies x sub 0 squared to the p minus 1 over 2. Actually, let's put it this way here. So I can square both sides of this. This one will go to 1 p. And again, this plot square to the power of p. Actually, let me go back with what I said before. No. Let me rewrite this. This is equivalent to saying actually x sub 0 squared to the power p minus 1 over 2 is congruent to 1 on. But we have x0 squared is congruent to a mod b. Remember, because we have assumed that a is a quadratic residue and x sub 0 is a solution. So this implies, together with this implies that the replacing the x sub 0 by a, so this implies a to the power of p minus 1 over 2 is congruent to 1 mod. And this is actually what we, Euler's criterion is stating. All right? Again, we're gonna, because these are congruent to each other, and this one is congruent to 1, so the 8 is to the power p minus 1 over 2 is congruent to 0. Let's go the other way around. All right? Let's assume that that condition is satisfied. Right? So let's assume that a to the power p minus 1 over 2 congruent to 1 mod e. And I want to show that x sub 0, to show that x squared congruent to a mod b has a solution. This one we're gonna take a let R be a primitive root of P. Then we know that A is going to be congruent to R or K mod P for a unique integer K. Such that K is between 1 and P minus. Now, let's raise both sides. Of the congruence A congruent to R to the K mod D to the P minus 1 over 2 half. So kind of we want to bring this congruence together with this to build in something that we can work with. So this becomes A, the left side, P minus 1 over 2. And this is congruent to R to the K, P minus 1 over 2 mod. And since this one is congruent to 1, so also this implies we have 1 congruent to A, P minus 1 over 2, congruent to R, K, P minus 1 over 2 mod. Let's concentrate on the first one and the last terms of this congruence relation. So we have then R to the power K, P minus 1 over 2 is congruent to 1 mod P. Now, remember that we have the order of R relative to P, all right, because this is a primitive root, this phi of P, and this is P minus 1. And together with a new exponent for R, this exponent also make R go to congruent to 1 mod P. So these two imply that P minus 1 divides K times P minus 1 over 2. And this in itself implies that K P minus 1 over 2 is a multiple 1 times L for some integer L. Or well, let's simplify this. So we can cancel the P minus 1 from both sides. And this implies that the K is equal to L. Now let's go back to the original equation in here. So we have R to the power K. We know that this one was congruent to A, right? Mod P. Now substitute for K becomes R to the power 2L is congruent to A mod P. Or rewriting this as R to the L squared is congruent to A mod P. And this means that X equal R to the L is a solution to X squared congruent to A mod P. All right. Therefore, the net result in here, we have A is a quadratic, of course, a residue of. So if the condition is satisfied, Euler's condition, then A becomes a quadratic residue. Now let's look at the corollary, which tell us, when A is quadratic non-residue. Here is the corollary. Again, same hypothesis, B a prime, an R prime, and A, an integer, relatively prime, to B. Then A is a quadratic. Non-residue. Of P if and only if A to the power P minus 1 over 2 is congruent to negative 1 mod. All right. So let's go ahead and actually prove this. Again, since greatest common divisor A and B is equal to 1, then by Euler's theorem, we have this congruence relation holds mod E, and this means A to the power B minus 1 is congruent to 1 mod B, and again this is equivalent to A to the power P minus 1 congruent to 0 mod C. Now, since P is odd, implies P minus 1 is even, and this implies we can factor the left-hand side of the last congruence as that. You can write it as a difference of squares, because this is actually, you could write as 2k if you wish, but we don't want to make the change of variable and so on. We will have it figured out altogether. So this congruence right here, okay, it factors into A P minus 1 over 2 minus 1, A P minus 1 over 2 plus difference of 2 squared. But also this implies that B is going to divide this product and since P is a prime, so it's going to divide either one of these this implies P divides A to the P minus 1 over 2 minus 1, or P divides A to the power P minus 1 over 2 plus 1. All right? It's going to divide either one of these, but not both. Not both divisibility relation. Oh, only one. And the reason for that, because if we have both P divides A P minus 1 over 2 minus 1, and P divides A to the power P minus 1 over 2 plus 1. This implies we could change these to congruence relation back into congruence relation means that A P minus 1 over 2 plus 1 is congruent to 1 mod D, and the other one say that A to the power P minus 1 over 2 is congruent to negative 1 mod. But since the left-hand side of these two congruence relations are the same, this implies 1 is congruent to negative 1 mod P, and which makes that P divides 2, which is a contradiction, because P is an odd product. So we only have one. Now, we have shown that if, by the theorem, by theorem 9.1, we have A is a quadratic residue of B if and only if A to the power P minus 1 over 2 minus is congruent to 1 mod P. And this, of course, is equivalent to the first one, P divides A to the power P minus 1 over 2 minus. Then the other one is going to be satisfied, hence P is going to divide A to the power P minus 1 over 2 plus 1 if and only if A is a quadratic non-residue. Of B. And this condition, of course, is equivalent to saying that A to the power P minus 1 over 2 is congruent to negative 1 mod P. And this takes care of the lab. All right? Now, let's look at an example. And with this example, I'm just going to illustrate other ideas that we will need to prove. Here is an example. Take P equal 30. And we need to find the we're going to apply Euler's criterion to find the integers that are quadratic residues of 30 and non-residues. We only need to consider the integers between 1 and 12. All right? Because any other integer, as we will actually show in the next remark, they're going to be, if two integers are congruent to each other, then if A is a quadratic residue, then the congruent number to it is going to be quadratic residue. Similarly for non-quadratic residue. We're going to state this is as a remark. So in other words, we need to concentrate on this. So we're going to calculate for each one of these, all right, for all these integers, all right. But I don't want to do the whole thing in here. 1, 2, 3, 4, 5, 6, up to 12. 7, 8, 9, 11, and 12. Then we're going to calculate the this A to the power B minus 1 over 2 mod B. Mod 13, of course. Mod 13. All right, so I'm just going to write these results. I guess we could do this one. This gives you 1, this gives you 12, the 3 give you 1, 4 give you 1, 5 give you 12, and this one give you 12, and this one give you 12 in here, 12 for 8, 1 for 9, 1 for 10, 12 and 1. Now, of course, the 12, this is congruent to negative 1 mod 13. All of these 12 is give you negative 1. All right, so the quadratic residues of 13 are 1, 3, 4, 9, 10, and 12. The quadratic non-residues there are 2, 5, 6, 7, 8, and 11. And you can find that there are 6 quadratic residues and 6 quadratic non-residues. And actually, this is the case in general, and we're going to prove this fact. Also, we're going to find that the quadratic residues, these are going to be congruent to half of these squared. In 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, in some order. So these are going to be the quadratic residues, all right, which is 1, 3, they say 1, 3, 4, 9, 10, and 12. All right, this one is congruent to 1 square, 2 square, sorry, 2 square, 3 square, 4 square, 5 square, 6 square, and mod 13 in some order. And even actually, this is a little more general. We're going to have this one is even more general. We don't have to take only a reduced residue, or what we call a complete residue system. That's the least non-negative residue system. All right. So let's first make the remark concerning two integers. If they are congruent to each other, then their residue or non-residue character is the same. All right? So here's the remark. And let I want to concentrate again on our problem, even though this is true for any integer, that B be an order prime. And A, B are integers. Relatively prime. To E, then if A is congruent to B mod E, then A is a quadratic residue of B of B, or I want to state two statements in one, or quadratic non-residue. If and only if B is a quadratic residue or none. And only if B is a quadratic residue or B or non-residue. Of course, quadratic. Okay, the proof of this is very, very, very simple. If you translate this into, of course, the language of solving a quadratic, simple quadratic equation. So I'm just going to leave this out for you to prove. All right. So now I want to determine, it's very important to determine the character of an integer, if it is actually a quadratic residue or not. Okay, so we only concentrate on actually to determine if an integer A is a quadratic residue or non-residue. We only need to consider values of A in a complete residue system mod B. given in particular, we may only consider A or restrict A to these integers. Restrict A to 1, 2, 3, up to 3. Because we don't want to consider 0 because we say 0 is not a quadratic residue or non-residue. It's not relatively prime, and this is it. In other words, the least positive complete residue system model. All right. Okay, so from the previous example, we have noticed that half of the integers from 1 to 12 actually are quadratic residues, and the other half is quadratic non-residues. Also, we have a way of listing the integers that they are quadratic residues as the squares of the integers from 1 to p minus 1 over 2 squared, right? So we're going to actually prove this is in general, all right? So we have the following theorem. That B be an odd prime. Then p minus 1 over 2 integers from this set one to p minus 1 are quadratic residues of p and p minus 1 over 2 integers are quadratic non-residue. Moreover, the quadratic residues are the 1 square, 2 square, up to p minus 1 over 2 square. And of course, the quadratic non-residues are the other ones. When we square these and reduce mod p, it's going to be the quadratic, so not among this list, it's going to be the quadratic non-residue. All right, we're going to go ahead and prove this, and we're going to, in some sense, we sort of proved this or stated this in the previous in section 8.4. We're going to let R be a primitive root. Of P. And now we know that the distinct indices is let me say that the integers in this set 1 to up to p minus 1 relative to the base R are integers in the same set, are integers in the same set. So you take the index of any one of these integers is going to be just one of those, and when the A, if you run through all of these, the indices is going to run through all of these. All right, so this is one thing. Of course, the same in some order. Let me put this in some order. And I'm going to match, the index of 1 is going to be 1, index of 2 is going to be 2. No, it's going to be just a rotation of these or a permutation of these. Now, also we have, since there are p minus 1 of those, since p minus 1 is even, half of the elements of S are even, and the other half is odd. So half of these integers is going to be even, then the other one is going to be, of course, odd, and it's going to be half of those. Now, with this, now remember that in by a theorem, it's going to remind you what this theorem is. Theorem in section 4.8, sorry, 8.4 rather. We have this. We say that A is a quadratic residue. Actually, we did this is for even case residues, but for our case, it's going to be for quadratic. Is a quadratic residue if and only if D, which is the greatest common divisor of 2, which is the exponent of x squared congruent to A, that's for quadratic, and P minus 1, which is phi of n in general, okay, which is in this case, we know this is equal to divides the index of A relative to the base R. All right. Now, in our case, since we have 2 divides this, 2 divides the index, if the index is even. And there are P minus 1 over 2 indices that are even, which means this implies that e minus 1 over 2 integers in S are quadratic residues. Quadratic residues. Also, Q does not divide the index of A if the index of A is odd. And again, and there are B minus 1 over 2 indices that are odd. And this implies B minus 1 over 2 integers in S are quadratic non-residue. Alright, so this takes care of the first part of the theorem. The second part of the theorem is to show that the quadratic residues are the squares of these up to b minus 1 or 2 squared. This is actually an exercise. It's going to be assigned as an exercise, number 3. All right, part A of section 9.1. And this is on page 174. Okay. So I was going to go over this. I was going to leave it for you. All right. Next, we're going to show that there are any quadratic congruence equation. Either it's going to have it for an order prime. Okay. Either it's going to have no solution, 0 number of solutions, or exactly 2 solutions that are incongruent. And then one other thing we would like to finish with is prove the Euler's criterion using Dirichlet approach for proof of Euler's criterion. All right, so here it is. I want to make this as a remark because it's really very simple. Again, let P be an order prime. And A quadratic residue of B simply means that, all right, this one is equivalent to saying that x squared congruent to A mod B. This has a solution. So if we take x sub 0 is a solution to x squared congruent to A mod B, then P minus x sub 0 is another solution. And it is not congruent. It's not congruent to x sub 0 mod b. Well, let's say first of all proof of this remark. So let's consider first of all showing that b minus x sub 0 is a solution. So we're going to consider this. So I'm going to square this. This gives you b squared minus 2bx sub 0 plus x sub 0 squared. Now, when we take this as a congruence relation, this is the b squared is going to be 0, the p is 0, so this becomes x sub 0 squared. And we know that this one is congruent to a because x sub 0 is a solution mod b. So this implies that b minus x sub 0 is a solution. Is a quadratic, actually, we could say is a solution. Okay, is a solution. To x squared congruent to mod. Now, the other thing is we're going to show that that p minus x sub 0 is not congruent to x sub 0 mod. We're going to do this one by contradiction. So you assume it is. P minus x sub 0 is congruent to x sub 0 mod p. And this is equivalent. We can cancel the b minus x sub 0 is congruent to x sub 0 mod p. And this in itself implies 2x sub 0 is congruent to 0. So that implies that p divides x sub 0, and since p is odd, so we have p divides x sub 0. Well, and this in itself implies that p divides x sub 0 squared, and this implies p divides a actually, because x sub 0 and a are congruent to each other. All right, and this is a contradiction because a is relatively prime to so we cannot have that. All right, so that's in fact, so this is what we have to the conclusion is if a is a quadratic residue mod b or of b, so hence if a is a quadratic residue of b, then x squared congruent to a mod b has two solutions, x sub 0 and b minus x sub 0 that are not congruent. Let me say two incongruent solutions has two incongruent solutions. Now, by Lagrange's theorem, x squared congruent to A mod E has at most two solutions. So this implies x squared congruent to A mod B has exactly two incongruent solutions. Two incongruent. On the other hand, if it is not, then we have no solution. If A is a quadratic non-residue, x squared congruent to A mod B has no solution. So the net result of all of this, together with the very first theorem, which says that any quadratic equation has a solution if and only if x squared is congruent or y squared is congruent to D mod B, we conclude that a quadratic congruence equation has zero solutions, no solutions, or exactly two incongruent solutions. All right. And this actually is true, as I said, not just for R primes. That's the way we did it here. The proof is for R prime because it turned out that when we solve the quadratic equation for non-primes, composite numbers, it amounts to solving actually some system of quadratic equations mod primes, and putting the solution of the system together to give a solution for the composite number that has these primes as its prime factor. All right. So since that's the result is true in general, we might as well just state it like that. Okay. Once we take care of that part of the theory, then we are having the theorem proved in general. All right. The last thing which is left is a proof of the Euler's criterion using given by Burton. Okay, here is the proof of this is proof here of Euler's criterion. Well, let me go actually there's the proof of Euler criterion. It is a little longer than the previous proof, but it has its merit actually in shedding a little more light on the Euler criterion. All right, so here we're going to start like this. We're going to let A be a quadratic non-residue first.
a quadratic non-residue of an order prime and then we're going to choose, let C belongs to this set of integers, 1, 2, up to p minus 1. Then we're going to consider the linear congruence. Of course, this A quadratic residue, remember that this one is relatively prime. All right. Okay, so we're going to consider the linear congruence equation, which is Cx is congruent to A mod P. Since P is one of the integers from 1 to P minus 1, so it is relatively prime to P. And this implies that Cx congruent to A mod P has a unique solution. Let's say C prime. All right? And C prime also belongs to the same set. 1, 2, up to P minus 1. As integers there are infinitely many C primes, but when we reduce this to mod P, then it's going to be one of those integers. All right, now this so we have this C prime being a solution such that as a solution and hence we have C prime is congruent to A mod B. So this actually does hold this congruence relation. Now I claim that C prime cannot equal to C. All right? Well, again, let's do it by contradiction. Assume they are equal. So this implies this congruence which is this congruence right here, so I'm going to write it in the top, becomes this. So this implies the congruence, which is C prime congruent to A mod B becomes C squared congruent to A mod B. But this means that this implies C is a solution to x squared congruent to A mod B, and which make A quadratic residue. A is a quadratic residue of P. And this is a contradiction by the choice of C as being, the choice of A as a non-quadratic residue. All right, now we're going to apply this to every C, all right, in the set. So for every C, So therefore, for every C in this set, there exists a unique C prime in the same set such that C prime is congruent to A mod E, and of course they are not equal to each other, and C prime does not equal this. So this means that the set of these integers, therefore, we can partition the set of integers in this set. We call it S, which is 1, 2, up to B minus 1, into subsets which is Ci prime where I ranges between 1 and P minus 1 over 2. So we've taken pairs of these are not equal from here. This one has P minus 1 element, so we take in subsets which are consisting of two distinct elements, so there's going to be P minus 1 over 2 of them, all right? Such that, so we get about this is the subset such that the product of Ci prime is congruent to A mod P, and of course these are different, so the Ci, as for double emphasis, does not equal Ci prime. So with this, then we have a system of congruences that holds. Therefore, we have the following congruences. C1 prime is congruent to A mod B, and C2 prime congruent to A mod B, and so on, up to the last Cp minus 1 over 2, Cp minus 1 over 2 prime is congruent to A mod B. So all of these hold, they are the true congruences. Now we're going to multiply them out. Properties of congruences allow us to multiply these. So we're going to multiply them. And this gives us C1 prime, C2 prime, and so on. C P minus 1 over 2, C P minus 1 over 2 prime. And this is congruent to how many A's in here? A, up to A, there is a P minus 1 over 2 times. This is mod P. All right, the right-hand side, no problem. This is going to be P A to the power P minus 1 over 2. And this is what Euler's criterion has in it, mod P. Now, in the right-hand side, remember that all these C's, all right, and C primes, they belong to the integer, so Ci, we know that, and Ci prime, all right? The ranges between the integer from 1 to p minus 1, and they are distinct. And they cover the whole range of these numbers. So these numbers, they're going to be actually, this is going to be the same numbers as 1 to up to p minus 1 in some order. So the product is going to be the same as the product of 1 to p minus 1. So this implies the left side. So from here, we obtain the left side is going to be like this. And this is congruent to a to the power p minus 1 over 2 mod p. Now we're going to invoke Wilson's theorem. We have this product is nothing but, remember, this is also equivalent to saying that p minus 1 factorial is congruent to a to the power p minus 1 over 2 mod p. The left-hand side, by Wilson's theorem, is congruent to negative 1. So if we start negative 1, is congruent to p minus 1 factorial, but this is congruent to a to the power p minus 1 over 2 mod p. So we proved, and this is it, which means that the a to the power p minus 1 over 2 is congruent to negative 1. So this implies that a p minus 1 over 2 is congruent to negative 1 mod p. Now remember this one, when that's our choice, when n is quadratic, is a quadratic non-residue. So we took care of that quadratic non-residue. All right, the other case, when A is a quadratic residue, we need a slightly different argument, or actually a modification of this argument. So let's assume that A is a quadratic residue of P. Then, as we've seen, x squared equal to a mod P has exactly two solutions, x sub 0 and P minus x sub 0. All right. Now, so let's consider this. X sub 0 multiplied by P minus x sub 0. And this is equal x sub 0 P minus x sub 0 squared. And this is congruent mod P to negative x sub 0 squared mod P. And this is going to be congruent to negative A mod P. because x squared is congruent to a, because it's a solution. Now, we're going to remove the two integers x sub 0 and p minus x sub 0 from this set, from the set 1, 2, up to p minus 1. Now, all the integers in here, they are not going to be satisfying this. So there will be, okay, so when we remove these from this set, we obtain a set of p minus 3 integers. The remaining, just subtract 2, so you get p minus 3. Now we're going to group these together. These into subsets. Which is C, I prime. Again, such that Ci does not equal Ci prime, and the product of these is congruent to A mod P. Now remember that for these integers, but remember that we can't do this because these are going to be solutions of this coming from having this equation Cx is congruent to A mod P, and the solution of this is actually the Ci primes, where these are actually definite. All right, now let's consider the following. So we have this system again, similar to the first part. So we have this system. We have C1 prime is congruent to A mod P, and C2 prime congruent to A mod P, up to Cp minus 3 over to Cp minus 3, 2 prime is congruent to A mod P. So we have all these congruences. Add to this, actually, one more congruence, and that is this comes from here. All right? Actually, we're going to go all the way from here to there. Okay, so we're going to also have this congruence. X sub 0 P minus X sub 0 is congruent to negative A mod P. All right, so we take this one out. Now this time I'm going to multiply these congruences. Now remember that one other thing, that the X sub 0 or P minus X sub 0 is not going to be any one of the C's because we removed them, all right? So all of these C's is going to be the other numbers other than these. So all of these will be distinct. Now we multiply, and we obtain the C1 prime, C2 prime, Cp minus 3 over 2 CP minus 3 over 2 prime, and then we have x sub 0, and then p minus x sub 0. And all of this is going to be congruent to the a's in here, which is going to be a p minus 3 over 2 multiplied by negative a mod p. Again, these integers are the same as the integers from 1 to b minus 1 in some order. So when we have them multiplied, we can rearrange the product to this. And this is congruent to negative a to the power p minus 3 over 2 plus 1, which happens to be, of course, a p minus 1 over 2 mod t. The left-hand side is p minus 1 factorial, congruent to negative a to the power of p minus 1 over 2 mod p. Now, Wilson's theorem, it tells us that the p minus 1 factorial is congruent to negative 1. Now, if I put the beginning of this congruent to negative a to the power p minus 1 over 2 mod t, then I can multiply by negative 1, and then I get the statement of Euler's criterion. This for a quadratic residue of p. So when there is a quadratic residue, we get congruent to. All right, that would be it for this long section. In the next section, we're going to introduce a notation that make a formula with a quadratic and non-quadratic residues is much, much simpler. And this is called Legendre simple. All right, so we're going to stop right here.